All right, let's jump straight into this explainer. Today, we're going to demystify exactly how thermal engineers model air flowing through an ultra-compact, high-performance heat exchanger. Because, if you've ever stood next to one of those massive commercial air conditioning units and wondered how on earth anyone mathematically predicts the way air navigates through its complex metallic internals, well, you are definitely in the right place. To really grasp the scale of the challenge we're dealing with, we have to talk about this absolutely massive number. This represents the ultra-compact density of the Medea Carrier V816 HP condenser coil. It is literally packing a staggering 1,300 square meters of surface area into a single cubic meter. Now, just to put that into perspective for a second, a standard commercial chilled water coil usually sits at around 685 square meters per cubic meter. So this V8 unit, it essentially doubles that density, which completely changes the aerodynamic game. So here's the situation. You've got a unit with a gross frontal area of about 3.24 square meters, basically a really large coil wrapping all the way around the chassis. And that face is heavily blocked by this staggered array of corrugated aluminum fins and little 7mm copper tubes. It raises a pretty crucial thermodynamic question. How do we actually mathematically model the air flowing through this dense metallic maze? I mean, we obviously can't just pretend it's an empty box, right? Okay, so here's our roadmap for today. First, the V8 condenser puzzle. Second, defining hydraulic diameter. Third, method 1, local fin geometry. Fourth, method 2, global core definition. And finally, avoiding flow depth traps. Don't worry, we're going to break down all these complex equations into structured, really easy to follow steps. Let's kick things off with section 1, the V8 condenser puzzle, where we are zooming right into the microgeometry of a macro machine. So the air here has to squeeze its way through an incredibly tight fin gap of just 1.28 millimeters. And right behind those fins, you've got 7mm outer diameter, inner grooved copper tubes spaced out at a 14mm transverse pitch. This makes traditional fluid dynamics calculations extremely difficult, mostly because the air isn't just smoothly sliding over a flat plate. No, it's being aggressively squeezed, chopped up, and redirected every step of the way. Which leads us perfectly into section 2, defining hydraulic diameter, or as I like to think of it, the thermal engineer's ultimate cheat code. The really crucial thing to understand here is that hydraulic diameter isn't just some boring formula. It's actually this ingenious cheat code for translating a square maze into a round pipe. You see, all of our classic fluid mechanics formulas, like calculating the Reynolds number to figure out if your flow is turbulent or laminar, they were originally designed for water flowing through perfectly round pipes. The hydraulic diameter lets us take this chaotic rectangular fin gap and simply ask, okay, if this gap were a perfect circle, what would its diameter be? Now, what's really fascinating here is that there are actually two completely valid, yet totally distinct paths to calculate this diameter, and it all depends on what data you have on hand. On one side, you have the practical field guide approach, which looks purely at the local geometry of the fins. And then on the other side, you've got the more rigorous academic approach used by textbook authors, which looks at the core as a whole entire system. Let's dive right into that first one. Section 3, Method 1, Local Fin Geometry. This is your practical, visual field guide approach. Let's apply this using the exact specs from our V8 condenser. Step 1, we identify our fin gap, which, as we established, is a tiny 1.28 millimeters. Step 2, we compare this to the distance between the tubes. So that's the transverse tube spacing of 14.0 millimeters. Because that 1.28 millimeter gap is just so incredibly small compared to the 14 millimeter distance between the tubes, the passage essentially acts like two infinitely wide parallel plates. This step-by-step method gives engineers a highly intuitive rule of thumb. Your hydraulic diameter is simply 2 times the fin gap. Boom. By simply multiplying our 1.28 millimeter gap by 2, we instantly discover that our hydraulic diameter is approximately 2.56 millimeters. It is just such an incredibly fast, practical way to get a workable number when you're literally standing out in the field, or if you're just doing some quick preliminary design work on a compact heat exchanger. But what if you need more precision? That brings us to section 4. Method 2, global core definition, the rigorous textbook academic approach. So instead of just looking at one single fin gap, this method forces us to zoom way out and define the entire bulk compact core using some specific volume and area variables. First, we need the minimum free flow area. That's the actual open space left after you subtract the thickness of all the fins and tubes from that 3.24 square meter frontal face. Then we define sigma, which is just the ratio of that free flow to the frontal area. And finally, we map out the total physical volume of the core, as well as the total heat transfer surface area packed inside of it. Once we have those big macro variables figured out, we can just plug them right into this beautiful, elegant formula to calculate the exact hydraulic diameter for the entire cross-section of the condenser. So the hydraulic diameter equals 4 times sigma, multiplied by the ratio of the core volume to the total surface area. And what makes this formula so incredibly powerful is that it inherently accounts for every single microfeature of the coil. Every little slit in the fin, every single tube intrusion, it averages all of it out across the entire matrix. All right, moving to our final section, Section 5, Avoiding Flow Depth Traps, where we need to resolve a very common mathematical misconception. I really cannot stress this enough, because there is a massive trap here. You absolutely cannot use the flow depth, the dimension that's usually labeled L, to calculate the 2D cross-sectional opening. It is so easy to get confused here because L definitely shows up when you're trying to figure out how much pressure drops as air pushes through the 3 rows of this condenser. But it absolutely, positively does not belong in the direct cross-sectional hydraulic diameter equation itself. This right here is exactly why understanding the physics behind the formula is just as important as doing the math itself. Flow depth only dictates the total volume and the total surface area. The hydraulic diameter describes the geometric opening that the air actually enters, not how far it has to travel once it gets inside. So look, when you're running these calculations for a super dense unit like the 16 HPV8, just always make sure your L variable stays firmly in the volume calculation where it belongs. Mastering both of these calculation methods, the fast local rule of thumb and the rigorous global K's and London approach, it really does make you a vastly better thermal engineer. You can now reliably model exactly how air is going to behave when it's forced into this ultra-dense 1,300 square meter per cubic meter environment. But it kind of leaves us with this really exciting final question, right? As we keep demanding more and more cooling capacity from smaller and smaller footprints, how much further can we push these microscopic hydraulic diameters before the aerodynamic friction becomes so great that the air simply refuses to flow? Honestly, that is the bleeding edge of thermodynamic design, and definitely something to keep in mind the next time you walk past one of these massive systems.